time to explore some circles. We'll start off talking about areas and circumferences, and in particular, not the full area of a circle, but a wedge of a circle, a circular sector. And not the full circumference of a circle, but part of a circle, part of the distance around the circle, just the arc length. So we'll do those two things. First of all, we know that the area of a circle is pi r squared. So you give me the radius, and I'll square that radius and multiply it by pi, and you get the area of a complete circle. Now let's suppose that we just want part of the circle. Like, for example, let's suppose we want this part right here. I'm leaving off this little wedge. Now this thing is divided into eighths. 1, 2, 3, 4, 5, 6, 7, 8. Well, we want 7 of those, 7/8 of the circle. So what we would do is we would say 7/8 times pi r squared. So we get the fraction of it. We take the area and multiply it by 7/8. We want 7/8 of the area. Likewise, over here, we've got 6/8, 5/8, 4/8. That's half of a circle, right? So we've got pi r squared. We want 1/2 of that. So I just multiply it by a half. Here is 3/8 times pi r squared, 2/8, and 1/8 times pi r squared. That's how we get the partial area, the area of a circular sector. And you can look upon this thing right here as a sector of the circle. We just want part of that. Now, in general, here's the way we're going to do it. Notice, let's suppose I want this part of the circle. Now, the way I'm going to identify that sector is I'm going to say, okay, this is 90 degrees here, or pi over 2 radians. Okay, so the question is, well, how much of the circle is this little wedge? Pi r squared is the entire circle. This is a fraction of that. And in fact, this 90 degrees is 1/4 of the circle. So really what we're going to do is we're going to say 1/4 times pi r squared. But look, here's the way we can do that. We take the angle measurement, pi over 2, and divide it by the total number of, in this case, radians. So the total number of radians around a circle is 2 pi. 2 pi radians. What we're dealing with here is a fraction of that, pi over 2. So I say, okay, well, what fraction am I dealing with for this whole circle? Well, pi over 2 over 2 pi. That fraction of the circle, pi r squared. Now, if I reduce this, notice I get pi over 4 pi, dropping this 2 down. The pi's cancel, and I've just got 1/4 pi r squared. That's the area of that sector right here. Now, another way we could do it, we could say, well, let's use the 90 degrees. Well, the 90 degrees goes on top. 90 over 360. Well, that's 1/4 times pi r squared. So there it goes. 1/4 pi r squared. So you can either be in radians, and if you are, you'll take the radian measure over 2 pi. If you're in degrees, you'll take the degree measure over 360. Now, so here's one. Here's 30 degrees, and I want to get this sector. So I take 30 over 360 times pi r squared. And I believe that would be 1/12 pi r squared. Okay. So notice what we have here. We have, we just take the angle measurement, divide it by 360. Now here, I've got it in radians. We could of course go theta over 360 times pi r squared, if theta is in degrees. Okay, but if we're in radians, 30 degrees is pi over 6 radians, so we've got pi over 6 divided by 2 pi times pi r squared, and that's 1/12 pi r squared. Now, we want to go on now to talk about arc length. Arc length is very similar. We take the angle measurement, okay? So remember, the full way around the circle is 2 pi r, okay? So if you ask me, what is the arc length all the way around the circle? Well, it's 2 pi times r. Well, what if we just want this much of the circle? What if we just want this arc length? Well, that's 1/4 of the distance around. Okay, so here's what's going to happen. We've got theta over 180. Now notice, let me just clarify that down here. Notice how I got this. I've got 90 over 360, that fraction of 2 pi r. And when I reduce that, notice this 2 goes down to 180. This 2 and this 360, that just reduces down to 180 on the bottom, and the 2 divides out. So I've got theta over 180 times pi r, see, because the 2's gone. Or you could do pi over 2 divided by 2 pi, and notice the 2's cancel, and you just get pi. Well, you just get theta r, because the pi's cancel and the 2's cancel, and you're just left with the theta r. So this is the arc length. Now remember, theta is not degree measure in this case. It's radian measure. Okay? Radian just tells you how many radius length measures there are on the arc. So you've got this many of these. Okay? So if theta were 2, you would have 2 times the radius length arcs. Okay? Now, what happens is, in this case right here for pi over 2, there are pi over 2 radius length arcs on this circle. That's how we get the arc length. Okay. Now, let's look at this. We want to find the area of the sector and the indicated arc length. Okay, so here's 40 degrees. So we take 40 divided by 360 times pi r squared. And it looks like we just get 25 pi over 9. Okay, now the arc length, we take 40 over 360, 2 pi r, and we get 10 over 9 pi for the arc length. Okay, 10/9 pi. Now we could convert this to radian measure. Just take the 40 and multiply it by pi over 180, and we get 2 pi over 9, and then we could use that 2 pi over 9 divided by 2 pi, and we still get, and multiply that by pi r squared, and we get 25 pi over 9. We get this back. But there's no reason to convert it. I mean, you might as well just say, well, what fraction am I dealing with? Well, 40 over 360. There it goes. Okay. Okay, now, I want to talk about some terminology here and just point out some things. When we're dealing with a circle, okay, so we looked at arc lengths and we looked at areas of circular sectors. Usually in geometry, when we're talking about a circle, we name a circle this way. We've got the center point here, and I name this one C. Okay, so I put a little circle with a dot in it and then a C, and we know, okay, I'm dealing with a circle here. It's sort of like when we talk about a triangle, we use a little triangle. Well, when we're talking about a circle, I use a little circle. So circle C, that's this circle. And what we've got here is we've got a central angle. These angles that are formed from the center of the circle, we call those central angles. This right here, 110, is a central angle. 130 is a central angle. Now notice this 110 extends out to point P and point M, okay? And we've got this point, or we've got this arc here that I'll call PM. And I just do a PM with a little arc over it. And that indicates that arc length. Now what we're going to say is, or that indicates that arc, not the arc length, that indicates the arc. Now, so this is arc PM. That's what that is. When I put an M in front of it, now I notice I need to just put an M there. I put an angle in front. When we talk about this PM, okay, this right here, and we talk about the measure of that arc, we're not talking about the arc length. We're talking about the measure of the arc. And what we're going to say is, since this central angle that captures that arc is 110 degrees, we refer to that measure of PM as 110 degrees. That's not how long the arc is. We just talk about that being the measure of the arc. Okay, it's a little more abstract than the arc length. Likewise, down here, notice we've got 130 degrees. So this arc here, the measure of this arc is 130 degrees. Okay, so we refer to that. The arc matches the angle here, the central angle, 130 degrees. Now, for this arc and this arc, those are both less than 180 degrees. So we refer to those as minor arcs. So PM and MN are minor arcs. However, this one, PMN, that's bigger than 180. We would refer to that as a major arc. Okay, so that's just some notation there. Okay. Okay. Now, I want to jump over here and take note of some things. I'm skipping this part here. I'm going to talk about that here in just a second. Or actually, let me just, the way I've pieced this together is I may do some rearranging here. But notice I've got some circles here, and I just want to use these circles to define something. Actually, let me draw it up here. Okay, here we go. Whenever you have a circle and you have a line that goes through like that, touches the circle at a couple of points, we call that a secant line. Okay, a secant. Okay. Now, if we just make it where we're looking at just a segment on the inside, like this. It doesn't extend outward. It's just a segment. We refer to that as a chord. Okay? So that right there is a chord. Now, if we have this situation, let's suppose I have a line that comes out here and it just touches the graph once. We call that a tangent. So notice, I've got a tangent right here. This line is a tangent to the circle. This is a chord, and this is a secant. Notice the tangent and the secant are both lines. The chord is a segment. So I want to explore some of these properties of tangents and chords and secants, that sort of thing. Let's suppose that we have a circle and we have a diameter. Let's suppose this is a diameter of the circle. Now the diameter of the circle is a chord that passes through the middle of the circle. It passes through the center of the circle. So let's suppose I have a circle here, and this is the center of the circle. Okay. This is the diameter. And let's suppose that this right here is a chord, and let's suppose that this diameter passes through this chord and a right angle is formed. Okay? When that happens, what you have is you have this segment and this segment are congruent. In other words, this chord gets bisected. Okay? It's bisected by the diameter. Okay? So whenever the diameter intersects a chord at a 90-degree angle, you know that that chord has been cut in half. Okay? So you notice here, and not just that, notice that this AD is equal to DC. Okay? That right there. Plus, also remember that the measure of this arc is equal to the measure of this arc. So AB and BC, they're equal. Okay? Okay? So let's look at that. Let's suppose that we've got a circle here. Here's the center. So we've got the diameter intersects this chord. And I want to find out what x is. Well, x, we just take the 2x plus 6 and set it equal to 8. Those are equal. Then we solve it, and we find that x equals 1. Okay? So that's something, we're just looking at some of the properties of these chords, and, you know, we're just exploring some of the characteristics about circles and chords and secants and tangents. This is one of the properties. Okay? Now, let's suppose that we have an angle formed this way. Let's suppose we have a chord and we have another chord. Okay? And they form an angle here at A. See? So you have a picture like this. Okay? There is an angle that's been made here. Right here is an angle. That angle right there is 1/2 of the arc that's been intercepted. Okay? So this angle, these two chords come up here. They form an angle here, and they intercept an arc. The measure of this angle right here is 1/2 of whatever this is. So if BC is 100 degrees, then the measure of angle A is 50 degrees. Now that's if this angle is on the circle, not the center. See, the center would just be exactly that measure. So if you're talking about the center angle, that would be 100 degrees. But it's not. It's this one over here on the circle. Okay? Now, let's look at this. So that's one of the properties. And rather than writing out the theorem, I just drew a picture of it. I think that might make more sense. Now, let's look at this one here. Let's look at the red. An angle A, this angle here, intersects BC. Okay? This arc is intercepted by angle A. And also, that same arc is intercepted over here by these two chords. Okay? So notice this angle here is created by these two chords, and they intercept this BC. Angle D, this angle right here, is created by these two chords, which also intercepts the same arc. When that happens, it means that this angle is congruent to this one. They have the same measure. Okay? So the measure of angle A is equal to the measure of angle D. Okay? Now you could go the other way too, and you can see that this angle right here and this angle are also congruent. Okay. Okay, there's that. Now, tangents. Let's look at this. Let's suppose that we have two tangents. And they come out here and they meet at a point. Now, so you come from this point and you come down here and you've got a tangent. You come up here and you've got another tangent. Well, what happens is, first of all, let's just think about a tangent. When a tangent comes up here and it meets a chord that comes up from the center of the circle, like this, okay? So it meets the radius. So here's a tangent. It touches the circle right here, and there's the radius comes up here and meets at that point of tangency. Whenever that happens, a right angle is formed. So there's a little segment that comes up from the center of the circle to a point of tangency, and where it meets that tangent, it's always going to be a right angle. Okay? So you can see that right angle here and here. Okay? Now, here's something that happens. You have this point, two tangents meet at this point. They are going to produce these two segments, these two tangents, from here to here, are going to be congruent. Okay? So from this point to this point, and from this point to this point, they produce these segments that are congruent. Okay? So that's something else to take note of. Okay. And also, this is very important. Right angles are formed here. Okay? Right here. From a segment from the center of the circle to that point of tangency makes a right angle. Now, let's suppose that we've got two secants. Okay? Two secants right here. And they meet inside the circle, and they form, the four angles are formed. 1, 2, 3, 4. The measure of angle 1 is equal to the sum of this arc plus this arc. See? Okay? So you've got angle 1, and you look at that angle that was formed by these two secants, and you look straight across at this arc, and then straight back the other way at that arc, and you see that angle 1, the measure of angle 1 is equal to half of that sum. Measure of angle 2, half of this sum. Measure of angle 3, half of this sum. And measure of angle 4, half of this sum. Okay? It's another thing to look at. Now, let's look at, okay, now notice that these secants intersected here inside the circle. Now let's look over here at, you have a couple of secants, and they intersect outside the circle. So I want to talk about this angle right here. CAT, cat. The measure of that angle is equal to this arc minus this arc times 1/2. In other words, half the difference. That's for intersections outside the circle. Now look at this one. Okay, this next one. Okay. So we've got intersections outside the circle. This time it's a secant and a tangent. Still, the measure of this angle right here is going to be half the difference between this arc and this arc. Now here's two tangents, same thing. We look at this angle right here, half the difference between this arc and this arc. Yeah, that's it. Okay, now I want to come back up here and talk about lines. Okay. And I'm looking down here at, we'll look at these lines. Okay. Whenever we have a circle, let's suppose that we have something like this. We have x squared plus y squared equals 25. This is a circle that has a center at the origin at 0, 0, and has a radius of 5. Now let's think about a point that's on that circle. Here it is, 3, 4. That's a point on that circle. Notice, let's see if it is. 3 squared plus 4 squared. Let's see here, that's 9 plus 16 equals 25. Yep. That's a point on the circle. If you take the x squared to take the x, square it, take the y, square it, add them together, you get 25. So that's a point on the circle. Now what I want to do is I want to get an equation. I want to get an equation for the line through the center of the circle and the point P. Okay? So in other words, what I want to do is I want to get an equation for this line right here. Well, notice that the slope, and this is at the point 3, 4. So notice that the slope, look at this, going from point 0, 0, I go over 1, 2, 3, and then up 4. 1, 2, 3, 4. So the slope is 4 over 3. That's the slope for that green. Okay? So there it is. Okay? 4/3. And notice that delta y is 4 and delta x is 3. Right? So the change in y is 4, the change in x is 3. Yeah. So look at this. We've got the point slope form of the line. Y minus 4 equals 4/3 x minus 3. Now, being able to write an equation for a line like this is very important. Now, remember the parametric form then would be 3t plus 3. See? 3t plus 3. See? The change in x times t plus the x coordinate. And then the change in y plus 4, like that. Yeah, there it goes. So this is the parametric form for the green line, and this is the slope-intercept form. Now let's think about perpendicular. Remember, the slope for the perpendicular is going to go like this. We flip the slope. Instead of 4/3, it's negative 3/4. Yeah, negative 3/4. So now we've got this. We've got negative 3, and we've got 4. See? Delta y is negative 3, and delta x is 4. Okay? So now let's take a look at that. Y minus 4 equals negative 3/4 x minus 3. Very simple. Okay? Now let's see how this would go. 4t plus 3, negative 3t plus 4. See? Because the bottom is the x and the top is the y. Yeah. And that will give us this purple. Now notice this purple is the tangent line. That's the tangent line right there. And remember, we said that a line coming up from the center intersecting the tangent is going to make a 90 degrees. So this is the tangent to the circle. So what we've done is we've said, okay, I want to get the equation for the tangent. And there it is. And here I've done two tangents. I've done a tangent here and a tangent here. Okay? So you could see that. You could say, well, okay, I've gotten this tangent. Okay, now let me look at this one down here. This one down here is going to be y plus 4 equals the slope. Let me see, the slope is negative 4 over 3, and then this is x minus 3, right? That's the equation for this line right here. Okay. So in other words, what we have here is, you could look upon it this way. You could say, okay, delta x is 3, and delta y is negative 4. Yeah, like that. Now we can flip it, or actually that would be, yeah, what I've got here is not the tangent. I've got this line. Here, let me put this back. So this line right here, that's what I got. See? So that's that line. Now, if we want to get the tangent, we would do y plus 4 equals negative 3 over 4 x minus 3. There we go. And that would give us this one. See? So all I did was I flipped it. Just flipped it and changed the sign. So that was negative 4/3, and now it is 3/4. Okay, so you can see 1, 2, 3, 1, 2, 3, 4. Yeah, and if you want the tangent, notice that the delta x for the tangent is going to be 4, and the delta y for the tangent is going to be 3. So then you could make the parametric form for these, okay, for this line right here. Okay, now let's explore this a minute. So let's suppose that I want to get the equation for this secant line right here. I want to get the equation for this secant line. Okay, so here's what I want to do. I want to say, okay, let's see what happens here. I'm going to go over 1, 2, 3, 4, 5, 6, 7. So delta x equals 7. And let's see what delta y is. Delta y is negative 1. Isn't that right? So let's see here. Actually, yeah. So let's count it off again. 1, 2, 3, 4, 5, 6, 7, and then down 1. Yeah. So delta y. Now you could get the slope. I could calculate the slope. I could say, okay, I'm going to take 4 minus a negative 3 over, actually, it's changing y over the change in x. So actually this is going to be 3 minus 4. Okay, 3 minus 4 over 4 minus a negative 3. And if I do it that way, I'm going to get negative 1 over 7. Okay, so I still get the slope of negative 1/7. So here's what we would have. We would have y minus 3 equals negative 1/7 x minus 4. There we go. Okay, and then you could do it. You could get a set of parametric equations: 7t plus 4 and negative t plus 3. Okay, and that's the equation for that. You could get this secant line, this chord over here, just by restricting the whoops. I don't know what happened there. You could restrict the domain of t. Okay. But anyway, that's, of course, in the parametric form, you just need to adjust the t. Maybe make the t go from negative 1 to 0 or something to get the chord. But anyway, that's what we want to pay attention to. when working through the assignment, those types of problems.